So in this video then, I'm going to run through a couple of questions on combined techniques. Now, this involves using information such as infrared, mass spectrometry, empirical formula, and so on, in order to work out the formula of an unknown compound. Now, at AS level, this is very much limited to IR, mass spec, and possibly empirical formula. At A level, this also encompasses NMR spectroscopy, but that's not something I'm going to be covering in this video. So, most important thing with these questions is, first of all, read all the information. So it gives you a percentage composition by mass. So this should be screaming out to you empirical formula. So let's put empirical. We can work that out in a minute. And then, apart from the regular preamble, identify compound C, make sure how it's linked to the evidence, it gives us a great bit of information here. In the mass spectrum, a secondary carbocation is responsible for the peak with the greatest relative intensity. So that means in my mass spectrum, this peak, which is the biggest peak, the greatest intensity, is a secondary carbocation. Now, that is very, very useful. And it has to be very useful because they've told us it explicitly. Which means if they didn't tell us this, it would have been hard to work out the answer. So it must play a key role. Now, the way I think that you should do this is essentially work it through. So I'm not going to use all these answer lines down here to do it in order. I'm going to show you what to do and how to write it down and set out your answer. So the first thing you do in all these questions, work out the empirical formula. Why? Because it tells you what the molecular formula is in a few steps time. So let's work out the empirical formula. Same method as normal. Okay, we're going to divide. So we're going to assume the percentages equate to grams out of 100. Divide 54.5 by 12, 9.1 by 1, and 36.4 by 16. I can tell you for nothing that equals 9.1. The other two are going to be slightly harder. 54.5 over 12 is 4.54, something, something, something. And the oxygen, 36.4 over 16 is 2.275. And now we just divide through by the smallest number. So we divide every number by 2.275. So obviously over 2.275 is going to equal 1. This over 2.275 is something else, and this is 2.275. So that gives us 1. 9.1 over 2.275 is 4, and I'm imagining the carbon is 2, but I would double check because it's good practice to double check even if you know what the answer is already. It's 2. Well, not quite, but basically 2. So that means the empirical formula is C2H4O. Now, why is that useful? Because if we now go and look at our spectrum, I'm going to leave the infrared for now because the mass spectrum is where I'm going to go next. Why do I go to the mass spectrum next? Because the mass spectrum gives me a molecular ion peak, and that peak looks like it's at 88. So C2H4O is the simplest whole number ratio. Now, I'm not a betting man, but I'm guessing that doesn't equal 88. What it does equal is 44. So the MR hit of this is 44, and my actual compound has a molar mass of 88. So that means my molecular formula is going to be C4H8O2. Okay, very important. Okay, now that is going to get you a bunch of marks right off the bat. That's the first 2 marks. Okay, at least the first 2 marks. Okay, you've worked out the empirical formula, you've got the empirical formula, you've linked the molar mass to the mass spectrum molecular ion peak, and you've used that value to go, well, if this is 44 and the total is 88, it must be double that. So I now know that my final compound has a formula C4H8O2, and that's the first things I put on my answer line. I would write down the empirical formula calculation, work out the molecular formula. Now we can start diving in to the infrared. Okay, now the infrared, you have a data sheet, which means you can very, very quickly assign, okay, these peaks. So big peak at 1680, a very sharp peak as well. It is definitely a carbonyl peak. Okay, that's almost in prime carbonyl territory, C double bond O. Just as a a bit of exam technique here. You don't have to write on the answer lines that the peak at 1700 indicates a C2O. You can just do this. You can just annotate your spectra. Okay, the examiners will look at your spectra, and if they are annotated correctly, there is marks awarded for in the same way as if you wrote it down. Now, the second bit is this broad peak here. Now, it's a broad peak at around 3000. Now, broad peak at this level is typically an OH peak, and it's possibly, because obviously it's on your data sheet, a broad peak in this region sort of suggests a carboxylic acid, COOH. And that actually matches up quite nicely with our molecular formula because we have two oxygens to throw in there. So we know we've got a C double bond O, and we've also got what looks like an alcohol peak that could be a carboxylic acid. So we think it's a carboxylic acid, which tells us where our two oxygens are, and we know it's got 4 carbons. Now, the rest of this question should be quite straightforward then, because you've annotated your spectrum, you've got the molecular formula, now we've just got to draw it, right? But hang on a minute, because C4H8O2 gives rise to a couple of options. So, for example, if I do it like this, if I do it as a straight chain, okay, nothing wrong with doing it like this. Here's my carboxylic acid. If I put all my hydrogens on, lo and behold, I have myself a correct structure. Or do I? Because there's another option. I can draw this a different way. What if I do 1, 2, 3 carbons, put the carboxylic acid on, and branch it and put a CH3 here? What's the difference? They are the same thing, right? So in terms of your answer, at this point, you're stuck. You don't know which one is which. If only they'd given us some extra information that I highlighted at the start of the question. Oh, look at that, there it is. A secondary carbocation is responsible. Now, from your time doing electrophilic addition and, you're looking at carbocations, a fragment ion that is produced as a secondary carbocation, if you recall, a secondary carbocation is a carbon that is bonded to 2 others and a hydrogen. So we're looking for this sort of group. This group must exist in the compound. Now, and of course, it must be bonded to something else that's also a carbon, but it obviously breaks there. So the fragment essentially has to look like that in the circle bit. Now, if I look at my drawings, only one of these drawings has that arrangement, and it's the bottom one, because you can see it right here, this C to C to C grouping. That's your secondary carbocation, because if, for example, I've just deleted my C there, if we fragment it here, the fragment ion that I get is C to C to CH3, positive charge, and there is your secondary carbocation. That is really, really important. You need to link your answer to that. You need to say that this is the peak, this is the fragment responsible. Okay, it's got a fragment, what is it, 41, 42. It's a fragment at 43, 12, 24, 36, 39, 41, 42, 43. This is the fragment for 43. It's this one. And it's the only one that works because there is no fragment in the first compound that will give you a secondary carbocation. They're all primary carbocations. So it cannot be this one, must be this one. And that's how you get that final mark, that 6th mark. You draw the actual structure of the fragment, link it to the peak at 43, and use it to justify your answer. Now, of course, all this needs to be on the answer lines, but you can lay it out exactly as I've spoken through it. Okay, as long as you lay it out nicely and neatly and you point out, and you can always write down on the answer lines what these peaks are. I like to just annotate the spectrum. As long as you're clear about what they are and what the assignments are and they're not ambiguous, examiners will give you credit. So I'm going to go through one more then. Okay, so it's going to give you another one, infrared spectrum, and It's another explain your reasoning, blah, blah, blah. Same idea, okay? More useful stuff in the question though. They always hide this stuff. Compound F is a trans stereoisomer. That's going to be useful later because I imagine there'll be two options that we can have. One will be cis, one will be trans. Gives you an elemental or spectral analysis, so let's go by the percentage composition again. First thing you do, empirical formula 68.6 over 12, 8.6 over 1, 22.8 over 16. We'll quickly work those out. So 68.6 over 12 is 5.7, 16, 8.6, and 22.8 over 16 is 1.425. Whoops, 1.425. Divide everything by 1.425 and we get 1. 8.6 over that is 6. And 5.716 over 1.428 gives us 4. So again, I'm going to rush through this a bit more because we've already done this once. So C4H60 is my empirical formula, so I'll just put it down here now. C4H60. And let's have a look at the molecular ion peak. The molecular ion peak is at 70. So again, let's just quickly, 4 times 12 is 48, plus 6 is 54, plus 16 is 70. So C4H60 is the molecular formula, okay, because this equals 70. So that is the molecular formula. Now, that explains the peak at 70. We've got a big peak here at 41. Okay, so I'll just put there 41. That might need explaining later. Now, let's take a quick look at our IR spectrum. So not a lot going on here. Okay, not a lot going on at all. So quite possibly a C to H, as you'd expect, but nothing else. And interestingly enough, there is another peak that we need to assign. There's a big peak here, same as the last one. Okay, telltale sign is a C double bond O. And that's all we can get from it. There's a C double bond O, and we've got C4H60, and it equals 70. The problem is, how do we work out the rest of it? Well, let's go back to the start of the question. I'm going to go all the way up. It's a trans stereoisomer. Now, what do we know about stereoisomerism? In order to be a stereoisomer, we must have two conditions met. The first condition is that we must have a carbon-carbon double bond. And the second condition is we must have two groups on each carbon. So now that limits us massively because that means one carbon has to come off this way, one has to come off this way. Okay, so we need different groups off each carbon. And now we have to try and make it work. Okay, so let's give it a go. And we also know we have to have a C double bond O somewhere. So let's put that in. It can't go on any of the two in the middle. Has to go on one of these carbons. So put a double O there, H there. Let's call it an aldehyde. It probably is an aldehyde. That gets rid of the oxygen. The remainder now just has to go on. So put a hydrogen here, that's 2. Here's 3. Put a CH3 there, 4, 5, 6. And there's my answer. It's a trans stereoisomer because the priority groups are on opposite sides. And if we want to work out how this peak of 41 gets there, so 70 to 41, okay, if I'm going from 70 to 41, I'm losing a large amount here. I'm losing 29. Well, let's say, where can I find 29 here? Well, I've got oxygen is 16, carbon is 12, hydrogen is 1, that's 29. And it does say the peak with the greatest intensity is caused by the loss of a functional group from the molecular ion of compound F. So I'm losing a functional group. I'm losing the aldehyde. So therefore, the peak at 41, which you can assign and you should assign, okay, you should draw it, is this. And you should assign that and you should say that the minus 29 is the aldehyde group that you've gotten rid of. Okay, or, positive charge. That's what you've gotten rid of. Okay, carbon to oxygen, hydrogen, you've broken it apart. 29 fragment is the aldehyde fragment, the 41 is the remainder. And that's it. Okay, you know it's a trans structure, so it has to be opposite. And the reason you can put both carbons, you know, on opposite sides, because if you don't put both carbons on opposite sides, it means you have to put two hydrogens on the same carbon, which means it's no longer a stereoisomer. The only way this compound works as a stereoisomer is if the carbons are on opposite sides. One must be an aldehyde because it shows you from the IR spec, and the rest is just putting the hydrogens in. So it looks like a really complicated setup, but in reality, it's very simple to work out if you just read the question. This bit, this first sentence, this first 5 words, okay, well 6 words if you count the letter F, tells you almost everything about it. Trans stereoisomer means carbon-carbon double bond. It basically, once you've worked out the molecular formula, it tells you what the structure has to be. It has to be carbon-carbon double bond, carbon-carbon. Can't be anything else. And then the rest is filling in the blanks. So hopefully that has helped you maybe figure out how to lay your answer out, what traps to fall into, how to analyze your spectrum, the importance of assigning fragment ions. Only do this at the end, by the way. Fragment ions are the last thing you should do. The order of attack you should do this in is empirical formula, molecular formula, then the IR, then the fragments if applicable. Okay, so that's the order I would put them in. So there we go. If you can get a good strategy down, if you can make sure you write everything down again, there are marks available for writing down your analysis. If you just draw the correct structure and move on, you won't get 6 out of 6. You have to do your reasoning and your working as well. You don't get anything. Okay, you don't just get all 6 marks for writing down the answer. You need to do more than that. You need to do your explanations as well. Just the answer will get you a couple of marks. Everything else is the important bit. So get a good rhythm, get a good routine for doing this, because these questions will also pop up in second year and they're much harder. So it's good to get into a system now, so when you get to them next year, you know exactly how your answer should be laid out.